Good afternoon, everyone. Welcome to the third lecture in a series of lectures on field and Galois theory. Today, Aadrita will be talking about Galois extensions. Aadrita, please start.
Yeah, so in our last talk, we had concluded by giving an introduction to separable extensions. So a separable extension was an extension K of alpha, L of K, so that we had any polynomial f over, let's start from all the definitions. So first we had, if f is a polynomial over K, then f is separable if it has no multiple roots. So in general, we take irreducible polynomials. Then we said, what about an element? So an element alpha in K is separable if minimal polynomial is separable. Finally, we called this extension L separable if all alpha in L are separable. Now we will look. Now we have looked at normal extensions, and now we have defined separable extensions. Now the question is, why are we interested in these types of extensions? So for example, we already have K over L, and say we have F, which is an irreducible polynomial over K, such that alpha in L and F is minimal for alpha. Then if L is normal, this implies that all roots of F are in L. And second, if L is separable, it says that all roots of F are distinct. So we see that if an extension is both normal and separable, then the polynomial F has n distinct roots in the extension L. So this is a good property that we would like to have. And next we see a proposition which says that we have K subfield of L, and characteristic of K is 0, then L is separable over K. Now, why do we look at this proposition? So we would like to see if any extension is separable or not. So in general, characteristic 0 extensions of characteristic 0 fields are separable. Now this actually, we expect this because when we look at fields like irrational numbers or real numbers, and we extend these, and what we finally get is that if we have an irreducible polynomials, it cannot have repeated roots. So this is just a generalization of that fact. And the proof is quite simple. So we have, say, the polynomial f in Kx, and say degree of f is n. And we can differentiate f to get f prime, and we have the degree of f prime. This is exactly n minus 1. And we see that f and f prime are co-prime. So this gives us the proof of the proposition. And we have crucially used the fact that this is characteristic 0, because when we differentiate, the derivative has exactly the degree n minus 1. It does not reduce more than that. But in general, this fails. This fails in general for characteristic k equal to say p not equal to 0. So say we have this polynomial f, then degree of f prime, this can be strictly less than n minus 1 for some polynomial f. And why does this hold? So if we write f as an x to the power n plus an minus 1 x to the n minus 1 up to a1x plus a naught, we see that f prime is n x to the n plus n minus 1 an minus 1 to the n minus 1 n minus 2 up to a1. And if this leading coefficient is divisible by n, so if p divides n, this implies that n times n is actually 0 in the field K. So we have the degree less than n minus 1. And so we cannot use this argument to talk about general fields of characteristic P. And in general, this proposition is not true. So let us, we have seen that any extension over a characteristic 0 field is separable. Now we would like to see an example of a field which is inseparable, because in our daily whatever we have worked so far, we can see that all extensions are separable. So we look at an example. So what we take is we take two fields K over L, and L is the field of polynomials in a single variable over a field small k, and K is k t to the p, and characteristic of small k is strictly positive. Then you note that t is a root of x to the p minus t to the p, which is in k t to the p x. So we have the field of all rational functions in a single variable p. We take a subfield which has the rational functions in t to the power p. Then the polynomial x to the p minus t to the p, which belongs to the group to the ring of polynomials over the field k, has a root t. Now this is a root in kt. Secondly, note that over L, we can factorize this, c to the p as x minus t whole to the p. Now this is just a simple application of the binomial theorem, where we can say that p divides p choose k, where k is not 0 or p. And this has all roots same. And so this is a irreducible polynomial which has all roots same in the sitting field, and hence we can conclude that this is not a separable extension. So in general, the extension need not be separable, but for our case, we will always assume that our extension is separable. Now we give another theorem in this line. So the theorem says that all extensions of finite fields are separable. So what do we have here? We have, we know that finite fields are of the form p to the m. So we have the field p to the m, which is a subfield of p to the f p to the n. And it's just very straightforward to conclude from here that these fields actually have all elements are the roots of the polynomial x to the p to the n minus x. And we know that this is separable because using the previous theorem, we can say that f prime is equal to -1 and f comma f prime. So the GCD is -1, and hence it is, and hence they are co-prime, so which is equal to +1. Doesn't really matter here because -1 and +1 are both constants, and hence we can conclude that this is a separable extension because they are co-prime, and the previous proof just follows. Okay. Now, we had looked at separable extensions and inseparable extensions, and we have also looked at normal extensions. Okay, and from here we can conclude another fact that says that if f is in K of x and a characteristic K equal to P, then f is separable if and only if there exists a polynomial g such that f of x equal to g of x to the power p. So this is a simple application. So when we factorize and so when we differentiate, then the coefficient gets multiplied by p, and other than the constant term, everything vanishes, and then we can say that f and f prime are co-prime, and then this holds. And in the opposite direction, if it is separable, then the two different polynomials f and f prime must have a GCD1, and hence this must be a function of the it must be a polynomial of x to the power p. So this is our discussion on the separable and normal extensions. Now we finally move on to defining Galois extensions. Before that, there is some terminology. First, the definition of Galois groups can be given in a lot of different manners. So we will use the definition from group of automorphisms. So we take a field K and we define automorphism group of K, which is the group of all automorphisms sigma from K to K, such that sigma is a field automorphism. And we can see that A is actually a group with the group operation as composition. Now we say that G is a group of automorphisms of K if G is a subgroup of K. So we need not deal with all the automorphisms. We can just deal with a small set, and in general we deal with a subgroup of the group of automorphisms. Now we have, say, let L be a subfield of K, then we denote by gal K over L the subset of A formed by automorphisms which keep L fixed. So it consists of all automorphisms sigma from K to K such that sigma of L equal to L for all L in L. So it is an automorphism which acts on the whole field, but it keeps the subfield L fixed. And we call this the Galwa group of K over L. And this is our definition of a Galwa field, a Galwa group. Now we would like to see what a Galwa field is. So we now define our Galois extension. So L over K is a Galois extension if it is finite, normal, and separable. And then this group is the Galois group. So we have given a definition using the terminology that we have developed so far, and the finiteness condition is actually given because in the initial study this finiteness helps in a lot of proofs, but there is something of the sort of infinite Galois extensions, and it has been extensively studied, but we will avoid that. So we will just deal with finite extensions and hence a finite Galois group. And what is a Galois extension? It is a field extension which is finite, normal, and separable. And there are some other equivalent definitions which we shall now discuss. So our main theorem is the following are equivalent. So what are the equivalent conditions? We have the following equivalent conditions. So first, obviously, we have this group extension, say K is a subgroup of M, and this is a finite extension. So we say M is normal and separable over K. So that is our extension is a Galwa extension. Then our second condition is M over K is equal to mod G, where mod G is the where G equal to Galwa M over K. Okay, so we have an extension and we define G, and just as an abbreviation, we say that the Galwa group of M over K is called G, and it is a Galwa extension if the degree of the extension M over K is exactly equal to the number of elements in the Galwa group. So this is the relation between the Galwa extension and the Galwa group. Third, we have K equal to M to the G. Now, what does this mean? This means that this is the set of points of M such that they are fixed under G. So we have a bunch of automorphisms in our group G, and we take the points which are fixed under all the automorphisms present in the group G. And in general, this is non-empty because 0 is fixed under all automorphisms. And why we can prove that this is actually a finite group, and eventually it is a field. And if these two are equal, then we say that this is a Galwa extension. And fourth, we have M is a splitting field of a separable polynomial. And these are the four conditions. Now we finally have a fifth condition that I would like to mention. So the fifth condition is, so suppose we have the group extension K and M, and take any field between these two extensions. And then we have here the same hierarchy. We have the trivial automorphism, then we have the our Galwa group and take any subgroup that lies between the trivial automorphism group and the whole Galwa group. Then we can map this L to Galwa M over L, so which keeps a group fixed which is larger than K. And similarly, we can take a subgroup H and we can map it to M over H. So we can map it to the fixed ones. And that is a field. Now, the fifth condition says that these two functions are actually inverses of each other. And this fifth condition is called the fundamental theorem of Galois theory. And we shall do this in our next talk. But today we will prove the equivalence of the first four conditions. What we will do is we shall show 1 implies 2, 2 implies 3, 3 implies 4, and 4 implies 1. So let's note that 4 implies 1 is a trivial condition. We can just show it trivially. So if M is a splitting field of a separable polynomial, it is separable over the field K. And since it is a splitting field, it is normal. And so the implication is trivial. Now, before proceeding, we can look at a few examples. Okay, so suppose we have a group G and a field M, then we can take a group action G acts on M and then M to the G over M is Galwa. So we give this example using our previous, assuming our previous equivalence. So we just take the elements of the fixed elements, and since that implies that the group is Galwa, the extension is Galwa, we say that this extension mg over m is Galwa. Now, suppose concretely, say we have the field m over k x1 up to x5. So we have five variable rational functions over a field K, and we take our group G to be S5. Then M to the G is actually K E1 to E5. So we have 5 elements, and these are actually denoted by E1 equal to summation xi. Then we have E2 equal to x1, x2 plus x1, x3, and so on, all the double numbers up to x4, x5. And we have E3 taking x1, x2, x3, and so on. E4 is 4, x2, x3, x4, and finally E5 is x1, x2, x3, x4, x5. So these are the 5 elements, and the fixed group is actually the rational fields over these polynomials. It follows that m over mg is S5, and in particular there is nothing special about S5. We can take any Sn, and hence by the Lagrange's theorem we can take any finite group, and this works for them. So any finite group can be written as a Galois group of some field. Now this what we have seen so far is if we fix the Galois group, we can get a field extension. Now there arises a question: if we fix a base field, can we get a Galois extension? And it turns out that this is a very difficult problem. This is in fact open. So what we have done, fixing a Galois field, Galois group and M, we get an extension. Now the question is, instead of fixing the bigger group, if we fix the lower group, so if we fix the lower group, lower field, can we get a Galois extension? And as I said, this is not very trivial. This actually gives rise to the inverse Galois problem. So we have the group G and we want to see Galois of M over some K equal to G. So does there exist M? And this gives us the inverse Galois problem. In particular, the inverse Galois problem deals when K is equal to Q. And there has been a lot of study on this. And in general, I think the latest shed of light that was shed was by Grothendieck when he discovered a relation between this inverse Galois problem and something about bicolored graphs. And there was some work done on this giving Bailey's theorem. But there has not been much advancement in this area. Okay. Now let us come back. So now we will see, before proving the equivalence, we will need a lemma. So this says that we have a field extension K over M, and G is Galwa field of M over K. Then mod G is less than equal to M colon K. So recall that in our equivalence, we had the condition that if this is equal, then it is a Galwa extension. But in general, it's not an equality, it's an inequality. Now, more generally, so if you have K extension over M, and if you have an extension X, then the question is, how many automorphisms make this diagram commute? And in general, if we take X equal to M, we get the above equality. And so it turns out if we call this N, then N is strictly less than M over K. This is the general statement that we'll prove, and we'll get the above as a corollary. Okay, so what we do now, first you will note that K over M is finite. This is the proof. Then M is equal to K alpha 1 up to alpha n for some n, and this is a field because it's a finite extension. So we can make a chain like K alpha 1, K alpha 1 alpha 2, and so on up to M. And we take this extension X and we want to see for just a single element extension. Now note that if alpha is a root of P, so say alpha 1, this is a root of P1, and degree of K alpha 1 over K, this is actually equal to degree of P1. And hence the extension, the number of homomorphisms that make this commute is at most degree of P1. So it is at most the number of roots of P1 that are contained in X. So in particular, if we have all the roots, then the degree, this degree of P1, there are exactly n roots of degree P1, and hence we have an equality instead of an inequality. Now this we saw that the theorem holds for an extension by a single element, and so for each element we can, so for each extension we get something like a alpha 1 up to alpha L colon k alpha 1 up to alpha L minus 1, and multiplying all of these we finally get m over k is greater than equal to mod of g. And in general, the number of automorphisms from x to k to x, such that the diagram commutes, and as a corollary we get m over k is greater than equal to mod of g. So our lemma is proved, and now we shall look at the proof of the equivalence theorem. Okay, so first we shall prove how 1 implies 2. So what is 1 and 2? Just a recall. So 1 says m is normal, separable, and 2 says that the degree of the extension is equal to mod of g. So we here we have the separable extension, and we shall prove it in 2 steps. So first we use the fact that m over k is separable. Now this implies we have exactly m colon k homomorphisms from m to k closure, which is the algebraic closure, and this we call x. So we want to prove this. Now what we have, again we use the same technique as the previous lemma. So we have k alpha 1 up to and so on, and then we just, instead of x we put k closure, so that is the algebraic closure, and this is less than equal to k alpha 1 colon k. And so first you observe that alpha 1 is separable. This implies that P1 has exactly k alpha 1 colon k roots. And since it's separable, all the roots are distinct, and so it has a distinct number of roots, and we get the number, the exact degree. And second, since k closure is the algebraic closure, it has all the roots. And so we get this above equality. So we have proved this part. So the first point. And the second point, which we use, where here we use that this is normal. So this implies any homomorphism from sigma k over m to k closure, and sigma is from k to k closure, then sigma maps m to m. So we shall prove this. So what is our claim is that if we have any homomorphism from k to k closure, then if we extend it to m, then sigma maps m to m. The proof goes as follows. So note that M is a splitting field of some polynomials since it is normal, then P is in, so say the polynomial P in Kx, then sigma maps all roots to roots. So in particular, it permutes the roots of the polynomial P. And then, since M is the splitting field, M contains all these roots. And finally, we can conclude that M maps to M. Since M is generated by these roots and these roots map to themselves, so M is fixed under the homomorphism sigma, and therefore there exists exactly M, the degree of M over K homomorphisms from M to K closure, and all of them map M to M. And in particular, we can just say that we have all maps, all homomorphisms from M to M, such that the Galwa group has the exact degree of the extension. And hence we have proved our first claim that separable normal extensions give us the Galwa group. Now we shall prove 2 implies 3. So what do we have? We have K over M. So 2 says that if we have an extension K over M, then M colon K is equal to mod G. And 3 says that K is equal to the fixed point set of the group of homomorphisms. So first, since we have K over K and G is the Galois extension, so G is gal MK. We can write K subset of MG subset of M. So we could write K over Mg over M. And we can conclude that M over Mg has mod G automorphisms by definition. Now, we do the following. We check the degree of the extension. We have M over K, which is equal to mod G, which is less than equal to M over Mg, since it lies between these. And this is less than equal to M colon K. And since we have 2 inequalities, there must be an equality at all points, and hence we get the required equality. And hence we have M colon Mg is equal to M colon K. Now we see another point, M over Mg. This is actually equal to M over K times Mg over K. So this is why the multiplicative property of the degree of the extension, and hence this implies, this first equality implies that Mg over K is 1, and hence we have Mg equal to K as was required for our proof. And now for our final implication, we show that 3 implies 4. So what we have here is the extension K over M, and we have A equal to Mg. And the fourth implication that both claim is that M is a splitting field of a separable polynomial. And proving this will give us the first 4 equivalences. So what we show here is, suppose we have this extension K over M, and we say G is the Galwa group of M over K, and take an element alpha in M. Now look at all distinct conjugates of alpha under G. So say we call them alpha, beta, gamma, and so on. And in general, you note that beta equal to G1 alpha, gamma equal to G2 alpha, because they are all conjugates. So there exists such G1, G2 such that these elements are conjugate to one another. Now consider the polynomial Px, which is equal to, so we took an element in M, and we define the polynomial Px as x minus alpha, x minus beta, and so on. And why is this a polynomial? This is a finite extension, so the number of conjugates is finite, and hence this polynomial is the finite multiplication of linear factors. And we know 2 points. First, P is separable, that is alpha not equal to beta not equal to gamma, because we took distinct conjugates. And secondly, we note that P is fixed by G. So why is so? Because all the coefficients in P, first you know that all the roots lie in the conjugate. So when we apply the automorphism sigma over the elements of this polynomial, we just get a permutation, and since this is commutative, we can just rearrange the factors and we get the rearrangement of the linear factors of P, and hence we get back P. So in general, so the coefficients of P are in mg equal to k, and therefore we can conclude P is in K. So any alpha in M is the root of separable polynomial in Kx such that all of its roots are in M, and in particular we have obtained a splitting field of the polynomial P, and hence we have shown the equivalence of all the 4 conditions that are there so far. And that concludes the equivalence of the first 4 theorems mentioned here. So in general, we can use any of these 4 definitions to define a Galwa group, but in particular, the first is the most popular, and the 5th is the most used one. So the 5th is, as I said, the 5th is it's called the fundamental theorem of Galwa theory, and this we shall prove in our next lecture. So, thank you. That's it for today. Anybody has any questions?
I don't think there are any questions. So thanks, Aadrita, for the talk. Join us again on the next day for the next lecture, where Aadrita will prove the fundamental theorem of Galwa theory, and we'll see some more applications. Thank you.